Hi, everyone. I wanted to make a short video to answer the question, talk about the question, what is a matroid? Like someone was saying on one of the forums, what is this thing? I don't quite, it's like it has independent sets and how do we know? I want to say it's an abstract notion, and it's a little bit like asking, what is a graph? And so since we all, I think, are comfortable with graphs right now, let me talk about that and then try to relate that to the question, what is a matroid? Okay, so question, what is a graph? Well, what is a graph? A graph, G, is two sets. It's a set of vertices, V, usually that's finite for us, and a set of edges, E. So V is a non-empty finite set, and E is a subset of the power set of V. So it's a bunch of subsets of vertices such that every element of E has size 2. Okay, so this is a lot like the definition of a matroid. You define one set. In this case, for a graph, it's the set, you're given a set, which is the set of vertices. And then you get to take a bunch of subsets of that specifies some property. And in the case of graphs, the only property the subsets have to satisfy is that they consist of exactly 2 elements, okay? And there are lots of things that kind of are naturally graphs. So like that we want to represent as a graph, right? So examples of things that we represent as graphs might be cities and roads connecting them. So these edges are pairs, really pairs of cities that are connected by a road. Other things we might want to represent as a graph might be people and connections on a social network, etc. Maybe they're computers and which ones are connected by fiber optic cables. There are so many things that are sets of things and some pairs of them are connected, right? So a graph is this very abstract thing. It's a set and a subset of its power set where those subsets have to satisfy some condition, and it's that they all have size 2. Okay, so similarly, what is a matroid? Well, a matroid is a set M, or is a thing M that consists of, it's an ordered pair, a non-empty finite set that we usually call E, together with, and here the thing is, we can talk about what a matroid is in lots of different ways. And the first way we're going to talk about is a matroid and a set script I, where the elements of this set I, so I is a subset of the power set of E such that, well, now it satisfies 2 properties. One, every subset of an element of I is in, oops, I, so wait, that's a different, every subset of an element of, having problems here. Every subset of an element of script I is in script I. And 2, that weird property that says that if I have 2 elements of script I and one has more elements than the other, then there exists something in the bigger set that I can throw in to the little set. So this is my shorthand for union, I plus X, and that'll also be in script I. And we call elements of this script I independent sets, by definition, independent sets, just like in our definition of graph, where we have this set E, right, which a priori is just this set of pairs, unordered pairs of elements of V. We call those unordered pairs edges. Here we're going to call these weird sets in I independent sets. Okay, and the idea is that once we have independent sets, we can define things like dependent sets and bases and what we'll call circuits. So if D is a subset of E and D is not in this set of independent sets, we say that D is dependent. And we also know that two more definitions, a maximal independent set is defined to be a basis, and a minimal dependent set is a circuit. Okay, and what we talked about in the office hour yesterday and what's in the video lectures is that you can see if I define a matroid by giving you this non-empty set E and writing out all of its independent sets, that's a ton of stuff because every set I give you, I have to write down all of its subsets by that first axiom 1. Every subset of an element of script I is in script I. That's a pain. But actually, it's much more efficient then if I just tell you what the biggest independent sets are, so the maximal ones that aren't contained in any other independent sets. I say, well, so I'm going to just tell you what the bases are, and then if you know it's a matroid, you say, oh yeah, if that's a maximal independent set, I know if it's independent, I know all of its subsets are in there too. Okay, so I'd rather tell you about a matroid by telling you about its bases than by telling you about its independent sets, because it's really the same amount of information once you have the definitions, but you don't have to write as much. Okay, but similarly, once I have independent sets, I have dependent sets. Once I have, and I could tell you what the dependent sets are instead of the independent sets, right? I just sort of take the complement in the power set. Or I could tell you what the circuits are. I could tell you the minimal dependent sets, right? And so a matroid is this non-empty finite set E together with, and I can tell you about it by telling you about the independent sets, but it also always has bases, and I can tell you about it by telling you about the bases, and it has circuits, and I can tell you about it by telling you about the circuits. And then the two properties that the independent sets have kind of parallels for bases and circuits. And what you'll see in the video lectures is us working through some of the examples there, right? And so just like with the abstract graph definition, a lot of things are, or you want to represent them as graphs. The reason I want to introduce matroids to you in this course is that we've been working with 3 things that really are matroids, okay? We can represent them as a matroid. And those 3 things are sets of vectors, so for instance, the rows or the columns of a matrix, okay? Graphs, where then here for a graph, the E is the edge set of the graph, and the independent sets will be sets without cycles, okay? And in rigidity, The E is again the edges of a graph, and the independent sets are going to be the 2, 3 sparse, the 2, 3 sparse subgraphs. Okay, so hopefully this kind of intuitive thing helps. It really, really helped me to hear your questions, and then I sort of got like, oh, like this is what you need to know, and this is what I need to tell you. So this is where the teaching happens. It's that interaction. Keep the questions coming, please. All right, I'm gonna stop now.